Hello, welcome. Today we're going to be discussing hyperbolic trig functions. This is going to be very quick and dirty. That will deal primarily with hyperbolic sine, hyperbolic cosine, inverse hyperbolic sine, and inverse hyperbolic cosine, commonly called sinh and cosh. Now, I realize that this is often covered in a first semester calculus course, but in the spring, we had a disruption due to the pandemic, and certain topics may have not been covered in detail, and maybe some courses just didn't emphasize this. Now, I'll be covering this in a very quick and dirty fashion with an eye on being able to use these for trigonometric substitution integrals. So this is going to be a very, very fast, very, very directed coverage. So without further ado, let's go ahead and get started, and we'll go ahead and get this. This, of course, we'll start here, and then we will be actually going through some calculations, but this is a quick background. Now, the very first, how these are defined, hyperbolic cosine, or cosh, is defined to be 1/2 e to the t plus e to the minus t. And if you notice from here, first of all, hyperbolic cosh is going to be symmetric with the y-axis, because you can substitute t for negative t and get the same thing. And notice that's very much like the standard cosine function in that regard. Hyperbolic sine, likewise, is going to be an odd function because you can substitute, if you take negative t for t, you would just get the reverse of these two, and you would get negative hyperbolic sine. Now, this relation I circled right here, I recommend you stop the recording and attempt to prove this yourself, because it's a nice little algebraic exercise. Forget the x and y for a moment. So pause, if you will, try to prove this. And assuming that you've already done it, that's how it goes right here. Basically, if you square hyperbolic cosine, you do the standard squaring process, and note that the middle term, the e to the t and the e to the minus t, that get multiplied together, become a 2. When you do the same with hyperbolic sine, you get a negative here. And then when you subtract the 2, the e to the 2t terms and the e to the minus 2t terms cancel, and you get a 1 right here that comes from positive 2 minus a minus 2, which is a positive 4, divided by 4. So those terms cancel out, and we get that relation 1. Now, this is going to be an important thing here. Now, from 1, we go down to this key result. The key result, if you just add hyperbolic sine squared to both sides, we get this relation here. Now, if you've already studied trigonometric substitution, this should remind you of the 1 plus x squared relation that you have when you use the substitution x equal tan theta, or tan t, right here. Very similar. Now, and I'll go ahead and skip down to this right here. If we let x be hyperbolic cosine of t and y be hyperbolic sine, and we do have the relationship x squared minus y squared is 1, that is going to be the relationship you have on the sideways opening hyperbola. And one way to think about that is, you notice that the x can never be 0, and y be a real number is impossible. So this hyperbolic branch, right, this branch of the hyperbola right here, has the x being hyperbolic cosine, and notice the x values, they come down to 1, then they increase. So hyperbolic cosine by design, is always greater than or equal to 1. And that's going to be important later. On the other hand, hyperbolic cosine, hyperbolic sine, on the other hand, that y value can be anything. That's going to be important later on. Now, the next thing is that if we look at the definition, if we differentiate hyperbolic cosine, the negative comes down from here, and you get hyperbolic sine. And you differentiate hyperbolic sine, you get hyperbolic cosine. So unlike the circular standard trig functions, the derivative of hyperbolic cosine is hyperbolic sine and vice versa. So they're each other's derivative. So when you're making a substitution, you don't have that pesky sine problem that you might have if you use let's say u equal sine theta. And then, of course, the derivative of sine is positive cosine, but then you differentiate cosine, you get negative sine. You don't have to worry about that here. Now, the other thing, if you notice, is that if you look at the derivative of hyperbolic sine, it's hyperbolic cosine, which is always positive, always greater than 1. So what that means, since hyperbolic sine is differentiable everywhere, and its its range is the entire real line, its derivative is positive for all t. That means the function hyperbolic sine is increasing everywhere, which means it's 1-to-1 and has an inverse. That's going to be very, very important. So the hyperbolic sine function is an interesting one. So it has an inverse. So let's call it inverse hyperbolic sine. Okay. Now let's calculate what this inverse looks like in terms of t, because this is going to have an expression that's going to be important to us. So if you start with here, take the sine of both sides, use the definition for hyperbolic sine, then multiply both sides by 2, subtract, we get this equation right here. Now that might look kind of like, well, what? Well, it's not a big deal, because now let's multiply both sides by e dx, and we get e to the 2x minus 2t e dx minus, well, e to the minus x times e dx is a 1. Now, if we let u equal e dx, look what we have. U squared is e to 2x. U is e dx. This is a quadratic. Since this is a quadratic equation, we can use a quadratic formula. And to remind you of that is, we have ax squared plus bx plus c equals 0. We know that x is equal to minus b plus or minus b squared minus 4ac over 2a. Well, that's basically what we did right here. Now notice we have this 4 here. We have a minus 1. So we down to this. Now if we take the 4 and take it out the square root sign, it's a 2. The 2 can be taken out of the numerator and canceled with the 2 in the denominator. So eventually we get u is equal to this. But remember, the u was originally e to the x. And since that's positive, we want the positive part right here. Because if you subtract this, this will be negative, and you might think about why. Think of the magnitude of the square root of t squared plus 1 compared to t. This magnitude will always be bigger, so you can't subtract it and get something positive. So we have this that's greater than 0 always. And then we can, if we use the plus here anyway. So now, if we take log of both sides, we get this thing right here. Remember, that is how you can expand inverse hyperbolic sine. Expands to this. That's going to be important. Okay? Now, what you do is you calculate set x equal hyperbolic cosine inverse. Now keep in mind that we'll have to do a restricted domain because hyperbolic cosine is not 1-to-1. We might, say, well, let x be bigger than 1 and calculate the inverse over that restricted range and see what you get. So go ahead and work on that. Stop the video and then pick it up. So assuming that you've done that, here's what we end up with. Letting x equal inverse hyperbolic cosine, we take hyperbolic cosine on both sides. Using the definition, we do exactly what we did before. I'm going to go a little quicker since you've already seen it once. Multiply by e to the x. Now we have this thing right here. Division by 2. Now we do have to worry just a little because this only makes sense if t is greater than 1 or greater than or equal to 1. But we knew that to be the case because this is only going to be defined. Its domain is t is greater than or equal to 1. Well, that shows up here, and we now know what x is. So this is how you expand inverse hyperbolic cosine. Okay, so we have these two things right here. We have this, and we have this for hyperbolic sine, inverse hyperbolic sine, inverse hyperbolic cosine. Okay, now let's actually do a little bit of math here. I mean, that was math, but now let's actually do some. So now what I'm going to do to prep the trig integrals that we can use with hyperbolic cosine, and let's calculate derivatives. And the very first thing I want to do is let's find the derivative. Let's say d dx, or this just dt, of hyperbolic sine inverse. Now note, you could just do this and go back to our what we had earlier. We could just calculate this and use the chain rule. This is going to be easier to do implicitly. So this is a nice little application of implicit differentiation. So let's just go ahead and solve this. So let x equal inverse hyperbolic sine, and we want dx dt. So we take hyperbolic sine on both sides, differentiate. Now you take d dt on both sides. Well, this is going to be hyperbolic cosine of x. By the chain rule, we get a dx dt. On the right, we get a 1. So our dx dt is 1 over hyperbolic cosine. Now we could right, so we got that. Now you might be saying, well, wait a second. We know that hyperbolic sine of x is this, but note, we call this relation here. This is a relation that we really started with, this relationship right here. The hyperbolic cosine is 1 plus hyperbolic sine squared. So now if we take the square root of both sides, remember hyperbolic cosine is always positive, of t. Okay, that's with t, so let's just put it to x. So 1 over hyperbolic cosine of x is 1 over the square root of 1 plus hyperbolic sine of x. But remember, hyperbolic sine of x is t. And there you go. So there's your first derivative formula. So what we've shown that the derivative of inverse hyperbolic sine is this. And that's a very, very nice formula to have. Now, let's do an exercise. Assume t is strictly greater than 1, so there's no domain problems. So go ahead and work on that. And I highly recommend, if you work on that you do what we did here. Okay, now let's see what we get. So how I'm going to work on that is I'm going to use implicit differentiation. So I'm going to say x is this, like so. That's going to be t. Differentiate with respect to t. So we get hyperbolic sine of dx dt, which is what we're after. But remember, we're going to use the same trick we used here, except now, since we want to go ahead and solve for this in terms of hyperbolic sine, we know that hyperbolic sine is going to be hyperbolic cosine squared minus 1, square rooted. And this works out to be, remember, x is hyperbolic cosine of that, so that's going to be t squared minus 1. Okay? So we get two rather big formulas here. So let's recap. Important to recap. Okay, some important things here, and I'll just go ahead and say them out. First of all, hyperbolic sine is going to be natural log of t plus, have to be careful here, make sure that's correct, t squared, yep. Oh, I just remembered it. Very early on I screwed up. That should have been a plus. I was just thinking about that for a second, so there we go. So it's going to be the square root of t squared plus 1 got that. And then we had the derivative. And repeat what we get there. So and repeat what we did here. Okay, so those are going to be the important things. And then the other important thing, and we're going to actually use this here, is remember that what I call the circle relation here, the hyperbola relation. This is going to be important too, because this is often used to, we're going to be using this part right here to convert. If necessary. And that's what we need with the hyperbolic trig functions.